Okay, now we're moving on to essentially section 5.4, and we're considering now linear transformations on vector spaces that are not necessarily Rn or Rm, and we're going to relate those. So there's a lot of ways to do this, and I've decided to do it this way. So what we're going to do is we're going to start with two vector spaces. So I'm going to let V be a vector space of dimension. The dimension of V is 2, and W is a vector space of dimension of W is 3. So instead of doing the general case first and then specializing to an example, I thought I'd start with an example and really specialize back to the general case. And I think it's the better route for sort of getting a handle on what's going on here. It doesn't seem as abstract. Okay, so these vector spaces, which again might not be Rn or Rm, they might be P of n, or they might be some other the continuous functions on 0, 1. It could be anything. Okay, so the basis for V is the set of vectors B1, B2, which we'll call beta B. Okay? And then the basis for W is the set of vectors C1, C2, C3, which we're calling capital C. Okay, and now we're gonna inject into this linear transformations. So here's the idea: we start with this vector space V, and some arbitrary vector x in V, and then we have another vector space over here, W, and the linear transformation we've defined takes vectors in X and sends it to vectors in W. All right, remember up here, here's the transformation T. Up here we're working in crazy space, right? It could be anything. Those polynomials are the ones I always come back to. But the idea of linear algebra, and I've said this 1,000 times, especially to Kyle Fowler, everything comes back to a matrix. So here's what we learned last week. And I know it was a tough pill to swallow, but here it is. The dimension of this vector space is 2. So if you look at the coordinate vector for this x, and here let's let x be a1 b1 plus a2 b2, just some random vector which is defined by its basis vectors, and it's a linear combination of the basis vectors. All right, so this guy when you take its coordinate vector with respect to the basis b, it puts it in R2. Right? And this basis vector is what? Sorry, coordinate vector is just a1 comma a2. And just because I put it in this spot, so here's the vector, and this is a1, that's a2. Okay? So the linear transformation takes vectors in V to vectors in W, and it can be very complex and weird, but this change of coordinate thing that we learned before projects the vector x in V onto Rn, in this case n being 2. Okay, so let's see what happens over here. What's T of x? T of x is T of a1 b1 plus a2 b2, right? Because that's how we defined it. And whatever that vector is, it gets mapped down here, and in this case, it's actually being mapped to what? R3. because the dimension is 3. So this turns out to be the point t of x, sorry, the coordinate vector t of x, but that's with respect to the c basis. All right, so let's unravel all of this. Okay. So what we have now is t of x equals a1 t b1, because t is linear, plus a2 t of b2. Okay. Now, we're going to make this a proper example. So let's define t of b1 to be 3c1 minus 2c2 plus 5c3. So t takes a vector in v and turns it into a vector in w, which turns out to be a linear combination of the basis vectors in w. All right. And t is completely defined on its relationship to the basis vectors. So all we have to do is define these two things. T of b2 is 4c1 plus 7c2 minus c3. And this is the book's notation. It's a little weird, but I like it. So this is given. This is part of the example, right? Okay, so let's see what the image of this vector x is in w. Right? So here we go. T of x is equal to t of a1 b1 plus a2 b2, which is a1 t of b1 plus a2 t of b2, which is a1 times, what's t of b1? We just defined that. It's 3c1 minus 2c2 plus 5c3 plus a2 times 4c1 plus 7c2 minus c3. Okay. So let's collect all these. So we have 3a1 plus 4a2 c1 plus minus 2a1 plus 7a2 c2 plus 5a1 minus a2 c3. And I told myself I was going to do this at the beginning, but I'm going to do it now. I want the c vectors to all be in red. Just to make it real clear where we're at, because we're now in W. Okay, so now I have, what do we have? We have t sub x expressed in the c vectors. And if you look at this guy, it's 3a1 plus 4a2 minus 2a1 plus 7a2, 5a1 minus a2. Right? So now we've taken this vector x, which was defined in the b basis, applied the linear transformation, brought it over to w, and we've now written it in the c basis. Okay, so this is just a matrix multiplication problem. If we pluck off the coefficients, and then multiply it by the vector a1, a2, this is a true equality. So this is a real equality, right? Okay, so the conclusion is that Tx of C is this matrix, I'll use blue, so I'm going to call M times A1, A2, which we defined above to be, where is it? XB, the coordinate vector. And so M turns out to be what? It's T of B1, so the coordinate vector of B1, and T of B2, that coordinate vector. Which are just column vectors. And so this matrix M, so definition, the matrix M is the matrix for T, transformation T, relative to the bases B and C. All right, so this is a commutative diagram. We use these a lot in mathematics. So I start with X, and this sends us to T of X via T. X is projected down to this guy. T of X is projected down to this guy. And to generalize things, this is in Rn, and this is in Rm. And how do you get from here to here? Multiplication by M. So this is a commutative diagram. And if V equals W, then we're back in section 4.4 with the relative change of bases. All right. So that's pretty cool. All we really need to do is pluck off, see here, the coefficients of the transformation, and that becomes the columns of our transformation matrix. So again, we start over here in V with a random vector, and we send it to W, but we don't like working in this realm. So instead we translate this guy to Rn and this guy to Rm, and then relate them by a matrix, because any linear transformation from Rn to Rm has a matrix assigned to it. We learned that way early in the term. Okay. Am I still recording? Yes. Note. In Rn, a matrix A is diagonalizable if the dimension of the eigenspaces or space equals n. We showed that last time. Okay, and so this leads to the only theorem from this section, So let's assume A is diagonalizable. So that A equals P D P inverse for some D that's n by n. And I'm going to write this. D is going to be a diagonal matrix such that the diagonals are the eigenvalues of A. Right? So, and B, if we let B be the matrix P1 down to Pn, which are, these are the columns of P, which are also the corresponding eigenvectors of A, then, using what we just showed above, the B matrix for T taking X to AX is D. And that's really cool. I'm going to let you explore that in the problems. But so if we went back up to this problem, then our M would be here. Our M would be the D from whatever linear transformation we defined. But it doesn't work here because this is not a square matrix. It's 3 by 2. Okay, let's do a fun example here. Give me a chance to introduce something cool. All right. Let A be the matrix 4 minus 9, 4 minus 8. Okay. Let's find the eigenvalues and eigenvectors of this guy. So the characteristic equation for A is what? Lambda squared plus 4 lambda plus 4. You set that equal to 0. And this says that lambda has 2 eigenvalues, which it always will, both of which are the same. So the algebraic multiplicity of lambda equaling minus 2 is 2. All right, let's see what the dimension of the eigenspace is, or otherwise known as the algebraic geometric multiplicity. Okay, so we compute now A plus 2I x, set that equal to 0. And this gives us the matrix 6 minus 9, 4 minus 6, 0, 0. And when you solve it, you get that x is equal to 3, 2. So note, the dimension of the eigenspace of A is 1, which is strictly less than 2. Hence, A is not diagonalizable. That's from the last section. But it's almost diagonalizable. So let's let B1 be this matrix we found, the eigenvector, right? This guy here. And just for fun, we're going to let B2 be this guy, right? And this came from this guy. Okay, and we're going to let B be a basis for R2. That's composed of these two vectors, B1 and B2. They're not multiples of each other, so they definitely span R2. So, okay, the B matrix for this transformation which is defined by this matrix up here. So for this transformation, which is T of x equals A of x, right? The B matrix for this transformation is a triangular matrix called the Jordan form of A. So now let P be these two column vectors. So P turns out to be 3, 2, 2, 1. Okay, and then you take this one step at a time, compute AP, which turns out to be -6, -4, -1, 0. And then compute P inverse AP, and you get -2, 1, 0, -2. So note the eigenvalues of A are in the diagonal, but it's not quite, it's not diagonal matrix, but it's upper triangular. So it's close to being a diagonal matrix, but not quite. You still get the same data though. You get the eigenvalues on the diagonal, but you wind up with a different characteristic equation. So this matrix is the B matrix for the transformation. And you're really going to have to sort this out through homework 7, which comes, the first part comes from section 5.4, 4, 6, 8, 9, 20, and 26. Not sure when it's due. I'm guessing next Wednesday. But we're about to jump into complex eigenvalues and eigenvectors, which can take a bit of time. So next Wednesday's the earliest, but maybe Friday. All right, hope you guys enjoyed that. We'll do well, I'm not sure how long this video is. Maybe 20, 30 minutes. We'll have time in class today, and I'll pick another one from homework, and we'll see how this plays out. Okay.